Good morning, everyone. Welcome to today's ASCE technical presentation. So we have three speakers today. The title of presentation is Lot Rating of DFW International Airport Taxiway Bridges for Jumbo Jet Aircraft Loads. So first, let me introduce the three speakers. They are all from console engineers. So Hyunsik currently serves as a console bridge group lead in Dallas, Texas. Hyunsik has 16 years of experience in bridge design, inspection, lot rating, and condition assessment. The second speaker, Peter Cao. Peter has over 20 years of experience in the transportation industry, currently serving as Console Texas Bridge Design Technical Practice Manager, overseeing all bridge design projects and operations in Texas. The third speaker, Saurav Neupane. Saurav has 7 years of experience in bridge design and currently serves as a project engineer at Console Engineers, specializing in complex bridge design and analysis. Let's welcome.
Thank you. Good morning. As Lucas introduced, my name is Hyunsik Moon. I'm with Console Engineers, and my colleagues and I are honored to be here to present for November Dallas chapter meeting, especially for this joint meeting with ASME Dallas Post. We're here to present our projects at DFW Airport and our findings, and hopefully some of you guys can find interest in that. Just a quick housekeeping item for those online joining us via Teams. If you could mute yourself through the presentation, we appreciate that. Well, we already got the intro, but just a quick intro. Myself, again, Hyunsik Moon. I'm with the Console Dallas Bridge Group. Peter, to my left, is the Texas Bridge Design Practice Manager, and Saurav Neupane is our project engineer. A quick agenda for today's meeting. We'll go through the project description and the goals, and then we will talk a little more in detail about our approach and load rating, as well as our analysis approach and findings. And we'll wrap it up with the results and the recommendations made to DFW Airport. All right, so project description. Everyone I'm sure here knows DFW International Airport. It's one of our major airports in the Metroplex. It was originally designed in the 1970s, so it's an aging infrastructure that's been in service for more than 50 years. It is the second largest airport in the US by land size, so it's got a lot of structural components within the airport. It has 7 runways, and the total runway length exceeds 80,000 feet or 15 miles in length. And those runways and taxiways are basically split by what we call the central terminal area. It's the International Parkway, northbound, southbound, the terminals. So the operation is actually split in the east and west side, and they need to be connected by a series of taxiway bridges. I don't know if you can see them, but there's 4 bridges here and 4 on the north sides. So what exactly are taxiway bridges? These are basically bridges for aircraft, for them to cross over the international parkways and the service roads and the AOA aircraft operation area roads. There are 8 of them over the central terminal area, 4 in the north, 4 in the south. They've been designed, between 1970s and 82s. They've been adding them basically as they need. And they're all comprised of steel tub girders with concrete deck and the steel bank caps. Those are NSTM. You used to know them as fracture critical, but the new term is now non-redundant stroke steel tension members. And they've been originally designed for 1.25 million pound aircraft back in the 70s. How many people here have structural background? Okay. How many of y'all done load rating in the past? All right, so quite a few guys already know what load rating does. What is load rating for those who haven't done it? It's just an analysis performed to determine the live load carrying capacity of a given bridge. So we are here to determine whether the bridge, the subject bridge have enough live load carrying capacity. Why would we load rate these bridges? Well, the aircraft, since the design of the airport, have evolved, and some of the modern aircrafts outweigh the design structural load. So that's a problem in airport operations to have airplanes that weigh more than it was designed for. Service life is another factor. It's been in service for 50 plus years. And they have already, through series of inspections, they have already determined some deterioration in the members. So basically, we're load rating to assess the bridge suitability under the new aircraft loads in their current condition. The aircrafts considered for this study, there are two groups, ADG5 and ADG6. These are airplane design groups that are grouped into different, a bucket of airplanes with certain weights and size configuration by FAA. We have Group 5 and Group 6. Just keep in mind, these are not all Group 5 planes and all Group 6. These were just handpicked by DFW Airport for this study based on their operation needs. Each of those airplanes, we basically looked up their manufacturer's documentations to figure out their different loading conditions, maximum ramp weight, maximum takeoff weight, landing weight, just trying to look at different configurations. On the right, you see the maximum ramp weight of all 9 bridges that were considered, 9 airplanes, excuse me, for all the for this study. It's kind of interesting that the as-built design load actually is only outweighed by one of the aircrafts that we consider, which was A380. I'm sure a lot of you guys are aware of A380 being the largest commercial aircraft, passenger airplanes, a double-decker. Outside of that, they actually weigh less than the design load. However, what we were interested in was basically the load distribution based on different wheel configurations. Bigger the plane, the more axles and wheels they have, and their loads are spread out better. Smaller planes, their loads are a little more concentrated. And how they act upon the existing bridge girder configuration, it was just hard for us to say these won't control, only these will control without doing analysis. That's why we have to look at the wheel configuration very closely. And the next slide basically shows all of the wheel configuration that was considered for the analysis. As you can see, they spread out pretty widely. I do want to mention that there was prior work on 2 of the 8 bridges along the central terminal area. Taxiways Yankee and Zulu are situated on the north side. They have been load rated in 2011. And from that study, they actually rehabilitated Yankee East and Yankee West in 2018 to accommodate the jumbo planes. So today, they actually do have capacity to carry these bridges on the north side of the airport. The expected outcome of the study was to basically do the same thing for the remaining 6 bridges. So we're trying to identify the load carrying capacity for the ADG5 and ADG6 aircraft for the remaining 6 bridges, and identify and prioritize rehabilitation needs, if any, for the airport. So I'll hand it over to Peter to go a little more in depth on load rating.
All right, so maybe we did a load rating before, exactly what ASCE says, and a lot of you guys have done load rating before, so you know exactly what equation I'm talking about. So look at the equation on the screen. It's complicated, right? I mean, there are a lot of terms, a lot of factors that we have to consider for the load rating, but it really is really simple. Like Hyunsik mentioned before, first we know the capacity, and that is true. Knowing the S bill, we calculate the concrete strength, that's on concrete strength, and the steel strength, and the composite actions and whatnot. So we figure out what's the capacity of each structural members. And then you take out all the dead load effects, because that is the portion of the capacity that is being used to carry a one step weight. So we take that out. So what you have on the upper side of the equation is the net load carrying capacity. And you take that divided by the life load. So you take the ratio. If the net load carrying capacity is more than the life load that you are analyzing or assigning, then you pass the load rating. If not, then you get a rating factor of less than 1, which means it doesn't meet the life load that you are analyzing. All right, so as defined by ASCE and TEXA bridge design, bridge inspection manuals, they are inventory and there's operating. So what that means is, for a new bridge design, we all design it for inventory, which means we use the full impact factors, we use the full life load, 1.75 life load, load factors. And if everything passed, so that means the bridge can be used by the design life load indefinitely without sacrificing the service life. And for load rating, inventory, because some of the bridges may not be designed in the past, 5-10 years, when we use LRFD. Some of the bridges, like the taxiway bridges, were designed in 1970s. So which means the code that the designer used back then was a lot different than the code that we use today. So, and then all the load factors and, going through all these years, a lot of things change. So, so what we want to do is consolidate all the information that we have and then put everything into one single number. So if the structure does not pass inventory rating based on today's code, and then we want to see if the structures pass operating. So if the structure failed inventory but pass operating, what that means is the structure is still safe to be used by the life load that you analyze. But to continue to use that structure with the life load that you analyze, it will shorten the service life. So that's basically the definitions of structures passing operating but not passing inventory. And of course, if the structure does not pass operating, that means the structure is not safe for the life load that you're analyzing, which means we need to load post the structures, limiting the life load going through the bridge. So that's basically what all these factors means. All right. So when you design a bridge, ASCE tells us what life load to use, gives us the wheel spacings, and then what is the distance between the lead axle and the second axle, or 14 feet, and then second to third between 14 to 30, and then give us the load as well. So what is that load? That load is really based on the study, based on statistical analysis, based on a lot of traffic going through the freeways and the bridges. And then ASCE said, okay, you know what? With all these wheel configurations, all this weight, I'm going to shoot a bell curve, and I'm going to cut it off at right here. And that is the load that we designed, which is the one on the left. That's very typical of what we designed in the previous. But is that what you see on the freeway? It may not be, right? There's some overweight trucks that you see on the freeways. If they follow the rules, they will get a permit if it's overweight. But if not, if they don't tell you, you may not catch them. So there are a lot of overload trucks on the bridge that we don't know about. And then also the speed. When we design the bridge, there's an impact factor. ESTO says 33% of impact factor that we use on all the bridges, regardless of speed or width or the kind of life that we design for, is all 33%. And that 33%, how did we come up with 33%? Again, it's a number that comes from statistical analysis. Used to be, if you guys have been in the industry for more than 15 years or so, back then when we used load factor design, the impact factor is not 33%, it's less 20 to 25% approximately. So the impact loads, we have the 33% impact load because on the bridges, there are a lot of potholes. So when the truck is traveling at 85 miles per hour, going through the pothole, it will hit that pavement and then it will impose a dynamic load on the structure. That's why we input impact load on the bridge design. So as a summary, those are the load factors that we use on the highway bridges. For the load factor that we use on load rating. For inventory, for the live load, we use 1.75, which is what we use to design a new bridge. And then for operating, it's 1.35, and then impact factor is 33%. All right, so now we switch gear from highway loadings to aircraft loading. So for aircraft loading, what we know for sure is from a manufacturer, we know what is the maximum wheel load that the aircraft can have. If not, the aircraft will not fly. So the pilot will know when everybody bought the planes, if a certain wheels is heavier than what the manufacturer say you can have, then somebody is getting off the plane or some cargo is getting off the plane. So it's very, very simple. So we know exactly what are the maximum loads and also the wheel spacing. Like Hyunsik said, all the aircraft groups that we define, they have a certain wheel spacing. It's not like highway loads where some truck may have maybe wider and the axle spacing may be different. But aircraft, they are defined. They are defined exactly by the manufacturer. So we know exactly what we are designing for. And also talking about impact load, talking about impact factor. Highway bridges, a lot of potholes, and some maybe less than the others, but on the taxiway bridges, typically they are better maintained by freeway bridges. So because if you got a concrete fall, somebody need to clean it up. If not, then that debris may get sucked into the jet engine and it may damage the jet engine. So taxiway bridges very well maintained. And then also the taxi speed across the bridge is not 85 miles per hour. If you go to DFW airport, you will probably see all these aircraft traveling across international highway, and they are slow. They are typically at 30, 40 miles per hour. So low speed and better maintained deck. All right, so it's a summary. For vehicular bridge, the uncertainty on the lifeline is high. Aircraft uncertainty is low. Speed on highway bridge is fast, and then aircraft is slow. And then pavement condition. One is kind of barriers for highway bridge can be bad, can be good when it's brand new. For the taxiway bridge, is general. In general, it's very good. All right, so Hyunsik mentioned about the work that somebody did in 2011 on the load rating bridges, stem taxiway bridges, and then there were some structural components that need to be rehabbed based on the study. In 2018, one of the taxiway bridge tracks got replaced. So during the design, the consultant did come up with a question on what is the load factors that they need to use to design the deck. And they had the same argument. For the aircraft loads, we know the loads, we know the wheel spacing. So do we still have to carry 1.75? That was the question that came up in 2018. And through some collaboration between the consultant and the owners, and we got involved as well. So through collaboration, and we all agree that 1.5 is the appropriate factor to be used for livelihood. All right, and then the last variable is impact factors. ASCE has 33% for highway bridges. So what is the appropriate impact factor to be used based on the low speed and better maintained deck? We went through some research on the technical journals. We look at ASCE and many other journals as well. And the lowest that we found on that we can justify on Hyunsik, it was 30%. So that's what we use on the load rating analysis. All right. So those are what ASCE specify to be used on highway bridges. And on aircraft, like I said before, loads are well defined, view spacing are well defined. So I want to tell the group. So if you were doing the design or the load rating analysis, what is the load factor that you feel comfortable in using? Apparently, we need to be more than one. So in fact, you like one is enough for my perspective. What about 1.25? Anyone feel 1.25 is sufficient? Raise your hand if you feel like 1.25 is enough. What about 1.5? Okay, you guys wrote the memo. Okay. Who feel like we still have to stick with 1.75 after knowing everything that I did? All right. 1.75, yeah. Yeah, we all like to be conservative, so I understand that. All right. So what we use on this study, on this project was use 1.5 for inventory, just like most of you agree. And then for operating, we lower it from 1.35 to 1.25 because we feel like we have more certainty on the load and the build spacings. And then impact, we reduce it from 33% to 30%. So overall, we kind of cut the conservatism by a little bit, 1.75 to 1.5, 35 to 25, and then 33% to 30%. So those are factors that we use in this project. All right, pass it to Saurav on the analysis part.
Thank you, Peter. So I'd like to briefly introduce our approach on the analysis of these breezes and the calculations we did to figure out the load rating of various components. So the first step we did was to review the as-built beginnings. We have 6 of the breezes in our study. They have the same design, but the same top girders have 8 different sections. And then the exterior girder and interior girders have slightly different sections. So we wanted to capture all of that in our model, in our analysis. So that was the first step. We reviewed as-built plans. And these steel top girders are welded to the steel bent caps as well. And the bent caps also have varying section properties along the length. So we tried to capture that. Second thing we did, and this is probably the more important of the two, is we did the field inspection to figure out what's the condition of all of these members. While doing our field investigation, we used D-meter to measure thickness of all the critical components along the length of the breeze at different locations. So this information is unique to all the 6 breezes and all of its top girders. We tabulated the results. What we found was there are certain locations where the section, we can see evidence of reduced section thickness, but it's not very much. It's a very small amount. We have captured that in our calculations. So in summary, our models and our analysis and calculation is based on the as-built, but modified as we observe in the field. After that, so we elected finite element analysis to figure out the loads from the 9 path on these breezes. There are different approaches, different kind of finite element analysis that we can do. We selected the Grilles model. So the Grilles model, in a sense, we represent each of the members using 2D beam. And we connect the 2D beams to form a 3D model of the whole structure. The rationale behind using a Grilles model is what we are looking at then. So we are looking at the positive bending moment, negative bending moment, and shear force for each of these members, whether it's still top or bend cap. And then we went on to load rate the deck as well as the columns and foundation. So this is the information we wanted to capture. So for this, we modeled the entire breeze, the steel top using the composite beam section properties as we find in the field. So for the boundary conditions, the column are supported on a footing cap that's resting on multiple drill shafts two drill shafts. So we have a fixed condition at the bottom of the columns. That's what we used. We are using pin connection at the ends of the girder, and the fixity of welding the steel tops to the steel bent cap is captured using the rigid links. We use partial rigid link to connect the bent cap to the columns. And the rationale here is that we are mostly interested in the vertical loads of the structure. So for the vertical loads, we have pin connection at the end of the girders, and then that together with the partial rigid links between cap and column will help us to capture the vertical load very accurately without making the model too complex. Because in the end, we need to run this model for different reasons and for many different iterations of aircraft loading. So that's what we did in terms of the area modeling on condition. So the previous model is well suited to capture the effects of the aircraft loading on the steel tubs and bent cap and foundation. But for the deck itself, because we use the composite section properties, it's not well suited to capture the forces on the deck as accurately. So we did a separate plate model for the deck using 6-inch by 6-inch mesh. And the deck itself is supported on a spring. We calibrated this coefficient of the spring using the prior model where we applied the unit load and then measured the deflection. And then back calculated the stiffness, and then we applied that over the length of the deck. So based on this, based on these two models, we did the load rating of steel top girders, steel bent caps, columns, deck and footing as mentioned. And then we extracted the bending moment, shear force, and axial force for the columns. This is just a sketch of what the results look like. This is for one aircraft. We have the loading for all the aircrafts for all the members, and we extracted all of that into our results. So finally, we calculated the capacity of each of these members using the latest ASCE code. So we calculated the positive bending moment capacity. We considered all the plastic moment capacity, the section properties of the components. We also included the locations and the spacings of the stiffeners, the girders, to calculate these capacities. We also included for example, for the negative bending moment capacity, we calculated the section properties, we excluding the reinforcement in the deck as dictated by the current ASCE codes. Similar for shear force. And then on the capacity found, we applied a condition factor. And the condition factor, the investigation of the breeze found the breeze to be in all the breezes to be in fair conditions. So the manual for breeze evaluation specifies a condition factor of 0.95. And this is supported by the reduction in thickness that we found as well. So we use condition factor of 0.95 to the capacity to capture the current condition of the breeze. And since we have multiple top girders, this is a redundant system. We use the system factor of 1 as specified in the breeze evaluation manual. So we have all the information now, all the loads, all the capacity, all the demand, and then we calculate rating factors for all the components. With that, I'd like to pass to Hyunsik for results and information.
All right, so we kind of went through how we load rated the bridges and then how we model these bridges in our final element model and how we calculate the capacity. And after that, it's just plug and chug into the equation and see what kind of rating factors we get. Again, as Peter mentioned, rating factor at the inventory level, that's the highest reliability level, and that's as if you got a brand new bridge, right? Rating factor greater than 1 at operating level, we're still good for utilizing that bridge. It's just that it doesn't have as high of reliability as inventory being 1.0, but still safe. So that's kind of at the least where we want to be. When it's below 1.0 and operating, that's when we got issues and we got to make repair recommendations and figure out how do we bring those rating factors to where to the target. So as you can see here, this is just example of our rating factor just for the superstructure for one of the 6 bridges. So all these different colors represent different aircrafts that were considered. Here is a cut line of rating factor equaling to 1.0. Anything to the right side of it, we're in great position. At inventory level, however, as you can see, some of them feel a little short of 1.0. That would have been ideal, but unfortunately, we did not have rating factor of 1.0 for every component at the inventory level. However, at operating, everything was above 1.0. So at the end of the day, all bridges are safe to carry the ADG-5 and ADG-6 aircraft that we studied. But because some of them fell under 1, by definition, those bridges are susceptible for accelerated deterioration. While all of the bridges achieved 1.0 in operating, we still recommended DFW Airport to rehabilitate these bridges to improve their capacity so that all the rating factors would be 1.0 or higher at the inventory level. That would help DFW Airport prevent deterioration or accelerate deterioration and increase their service life. So our recommended repairs included deck replacement. Those were insufficient depth and old rebars. The rebars that will go up and down instead of having continuous bar on top and bottom, which is outdated. So we recommended deck replacements. Some steel tub girder strengthening. Same thing in the footing. And if we were going to take these bridges out of commission and replace and rehabilitate the girders, that would be our perfect opportunity to take out the approach slabs and replace the backfill. The approach slabs and backfill don't really contribute to the rating factors of these bridges, but they have been problematic in the past as they've used native soil when they constructed these bridges, and you all know Irving soil is the worst in the Metroplex, and they have been there has been a lot of issues with expensive clay. So if they were to perform this rehabilitation, we would definitely recommend them to replace the approach slab as well as all the backfill. And I mentioned the Taxiway Yankee West and Yankee East have already been rehabilitated, and our recommendations are basically the same. So all 6 bridges kind of require the same rehabilitation needs, and DFW Airport has money. So if they wanted to repair all of them, they could if they choose to. However, taking these taxiway bridges out of operation poses a significant challenge in their daily operations. So obviously, we can't just close all 6 bridges and repair them at the same time. What we proposed was to maximize flexibility, the most return on their investment. And that was utilizing the already repaired North Yankee bridges and prioritizing the next repair in the south intersection so that the airport would at least have a crossing on both north and south parts of the airport, given whichever direction they land. And that way, they don't have to taxi around as much. And after discussing with the DFW Airport, we decided to prioritize taxiway bridges Bravo East and Bravo West, which are situated on the south end of the airport. So that concludes our presentation for today. We'd like to extend our thanks to DFW Airport for giving us the opportunity to work on this project and trusting us to be involved in this critical study. And with that, I'll open for questions. Yes, sir.
So, did you model the calculators as lining?
Yeah.
Yes.
So do you think, like, I saw like the inventory really was under one of the exterior and the interior, some of them. So do you think that you have used some other element type, it may have got across the line instead of a line element?
So.
Go for it.
Like each where I can bottom plane separately and
So the main thing that we're looking for here is the positive moment capacity, negative capacity of the shell, which is already a aggregate information. So even if we use a plate element, so even if we model plan separately, wave separately, right, we'll get the stresses and we aggregate those into pleasure components. So our rating factor would not have changed because the demand is pretty much the same in the direction, but it could increase the model complexity significantly. And we had to run this analysis many times for different impacts and all that. And in addition, these pieces are fairly spread. So there is not much like lateral components, creating forces and stresses. So that's why we settled on the line member. But then we also felt the need to refine it for the deck to capture the forces. So therefore, we only opted for the plate models of the deck.
So we did not drill down to the component level of the girder, but just overall capacity and overall load effects of the girders. Now, when we looked at the girder strengthening needs, we did look at the stress level of the bottom flange specifically separately, but for load rating purposes, we did not look at, say, bottom flange load rating and the webs separately. Just overall section capacity for the positive and negative moments.
So for your, sorry, a follow-up question. So for your rehab recommendation for the third girder, how do you identify it?
So we had the moment already at the points of interest that we basically MORS to figure out what stress we're at. Yeah. And how we needed to improve that in order to be above. Yes, sir.
So you mentioned that you have not made a superstructure, substructure and foundation, right? You present the result only for superstructure. So for substructure and foundation, are they all above one operating?
Yes, they're all above one. The one that was presented earlier was just for demonstration purposes. The deck is kind of highlighted here because that was the most, that was a controlling component of the entire bridge. So wanted to show that the substructure were in pretty good shape, as you would imagine. Yes, sir.
Have you done the another analysis, like to check how much maximum deflection it can take?
We did not include deflection calc in this load rating study. However, when we were looking at the abutment issues that we mentioned earlier, that is something that we did consider about the braking force. So it's still longitudinal, but we did not consider any other lateral forces in this load rating.
Yeah, the abutment issues for all the taxiways bridges, that issues been known since the late 80s. So we found some past projects from the DFW, and then a lot of studies been done since the late 80s on why is the abutment closing up. If you are involved in the project, you look at the deck, you can see that the expansion joints are shut, and then if the joint material sometimes being squeezed out of the joint. So that issue has been known for a long time.
Yes, sir.
You discussed the landing gear configuration briefly. Which aircraft was the worst? I think if I'm having a little trouble telling your colors there, but I think I know what it means.
So yeah, A380, 800 had the worst results.
It's the dark blue, I think.
Yeah, if you look at the deck, it's the W, which is the A380.
Oh, the 777s also had a low rating.
Yeah.
It's hard to tell which wheel configuration had the worst of. We did drill down to each component. So like we know how all the different wheel configurations impacted the decks
Yeah.
and then the girders and the substructure differently, but I don't think there was a consistent theme because the girder spacing controls the deck rating, right? Because girders act as, but then how the wheels come down to the girder level and the span configuration, you know, now it may be controlled by the heavier craft or how the wheels align with the girders themselves. So it was hard to, that's exactly what I was saying earlier. It was hard to just look at the wheel configuration and try to guess which one controlled because there's too many variables. So we just put our dumb hat on and just put the airplane loads in the model and just basically extract all the loads. Yes, sir.
So where did you get your loaded from the manufacturers or from the
They were obtained from the manufacturer. For each of the plane, we pull up their the aircraft characteristic, airport and maintenance planning. That tells you how to design their pavement for these loads, and then they'll tell you maximum takeoff weight, maximum ramp weight, maximum landing weight for how the loads are distributed between the nose gear and the landing gear. There's a whole set of numbers that we went through. Absolutely.
Yeah, I want to. So, then for the workplace bridges, we have like if you have any traffic loading that's higher than actually the engine can permit, right? So for these aircraft bridges, that are they operating the same thing? Let's say if you have any aircraft that's higher than A380, do they need to find a permit to cross the bridge or something else?
Yes, I don't know if you had the opportunity to hear his question. The question was for highway bridges, permits are required for heavy, overweight trucks. Are similar processes required for the aircraft loads on the taxiway bridges? And the answer is yes, it won't be a permit, but they need the airport's approval. But until this similar analysis is done and they're approved, they won't even be allowed to be in the bridge. So there's the airport operations know all the aircraft coming in. They'll know if it's an overweight aircraft request. They won't even accept it unless their airport engineers would have analyzed them and confirmed that the loads can be taken. This is basically the same scenario. They wanted to bring the A380s and the 747-800Fs, and they wanted to bring them into their operations, but they weren't sure. That's why they had to undergo all this study for them to get the warm and fuzzy feeling, and then allow them to be operated. And currently, only Taxiway Yankee is the only one they can cross. But soon after this rehabilitation, they should have access in Bravo also. Increasing their flexibility in operations.
Yeah, and plus, if there's overweight aircraft that are landing at DFW airport, doesn't mean that they cannot land at the airport. They only cross the taxiway bridge because they only cross the taxiway bridge if they land on one side of the airport and they want to get on the other side of the airport. So if they're not allowed to use the bridge, they can land at the airport, but they just land at the same side that they are stopping. They have to cross the taxiway. Yeah.
Yes, sir.
How do you determine like braking loads? So for anything that combination of national whatever airplane if they want to stop on the bridge. Did you analyze it?
Braking force, I don't think was as part of this analysis for load rating purposes. Now, if you were to design new bridges, it's a different story. But for load rating purposes, when we mostly focus on the vertical loads, we did not consider the braking force.
Yeah, so I want to touch on the braking loads. So in late 80s, the study that I mentioned earlier, it was a lot. They mentioned a lot about the braking load. There was an argument back then on what is the percentage of life load to be used on the braking load. I know EXCO and Techstar, they kind of changed along these years. And the EXCO says one thing, Techstar say, I don't think so. I want to use this. So there are a lot of argument on how much braking force to use. So there was there was a study back then in the eighties that how much braking will be used because they start seeing the expansion joint shut at the accelerator radius. So there was a study back then in the late eighties. But in this project, we only look at the vertical load, only all the moments and shear and stuff. We can look at braking.
And for columns, we only consider the axial force.
I want to say, after the question.
Yes, sir.
And more about that in the opinion. The old guys, I'll stand with the old guys. Designed this over 50 years ago. I think they did a pretty darn good job.
I agree.
I agree. And that's why
They
you,
had no idea. But that's pretty cool.
and if you think about it, all of the bridges pass at the operating level, meaning they're still safe to carry all these aircraft, including the A380s. They're safe. So I think they did I think at the time, the design level was probably well over designed, but for a good reason, you know, anticipating that the aircrafts are probably going to get bigger and heavier and trying to design for that ahead of time. So I absolutely agree with you that the original design was well designed. Yes, sir.
I was involved in the construction and some of the, that, you know, what it was designed for, what the load for, whether it's C5A out of Mississippi.
For these taxiway bridges, the design level was 1.25 million pounds.
5 million, but got a zillion different, Novo configurations.
Yeah, we did not, the as-built did not tell us the wheel configuration that was considered. That would have helped. That would have helped for sure, but they might have not, you know, justified the project. So it would have been lost on our part, but that would have helped the airport for sure.
You should have followed me.
Well, now that we're done with this, we'll definitely reach out to any future questions. Anything else? Well, we'll stick around. So if you have any questions, feel free to come by. But thank you for attending.